Today I want to talk about a topic that I came across just a couple of years ago and I had never imagined existed. And it's the question of bias and fairness, which again, as a computer science or computer vision person, had not quite crossed my path, but now it's quite obviously super important. And so I would like to start with a motivating picture. So all of us got into computer vision thinking that we are building, and I should say AI in general, so I think we're building technology that can help people live better lives. So it's very interesting from the scientific point of view. We want to know the fundamental laws of intelligence. We want to understand how biology realizes or builds autonomous systems that are successful, but also as engineers, we want to, of course, build machines that help people live better lives. And so this is the picture that is in my mind when I work on with my students. But then you read the newspapers and there is quite a bit of blowback, and you see articles in newspapers that are quite negative. And so this is one. Another one is we teach AI systems everything, including our biases. Facial recognition is accurate if you're a white guy. And here is AOC. AOC is a member of the US Parliament, which is called Congress. She says that white men are building AI and therefore AI is biased against everybody else, which is, a little bit insulting or worrisome in many ways, the statement. And so what's happening? And so clearly there is concern that AI is a powerful technology. And we want to make sure that AI is respectful to everyone and that we are working towards a more equal and just society. This is what we will want. And so the public is watching and it demands attention on our part. And so this is what, and so today I'm going to talk about what I'm doing about it myself. So first of all, why do we bring AI, machine learning into society? And the reason is that society institutions don't work super well. And so machine learning can help. And here is an example I got from the LA Times about a year ago. This was a case of twins, I think identical twins, who applied for asylum in the US. One got asylum, the other one didn't. And so this is when you see something like that, it makes your blood boil. This is clear injustice. And why does it happen? Well, probably because the paperwork ended up in front of different adjusters or different examiners who ended up with a different opinion on what to do. And so it's interesting to read this article in The Atlantic on, why do bureaucrats look so cold and uncaring towards people? And we all feel a little bit alienated in front of big bureaucracies, and maybe machine learning and AI can do something to make bureaucracy be more tailored towards the needs of people and understand better why are we there asking for something and administering rules in a more even-handed way and so on. So that's certainly one reason why we want to come into the picture. Another reason is that on specifics like face recognition, we know that humans feel very accurate, but in fact they are not. And so this is a picture taken from a famous case where this lady accused this guy in a police lineup of being the perpetrator of a horrible crime. He ended up going to jail for many years until somebody else exonerated him, confessed to the crime. And there is a report of the national academies in the US that shows that that witnesses are highly unreliable. And so I'm not going to go through the precision recall curves for the witnesses, but they're quite terrible. And there is a paper by Jonathan Phillips and collaborators, Alice O'Toole, as a senior author in PNAS, that looks at, compares the performance in face recognition between random people. So these are students at the University of Texas, the middle plot. So sorry, the vertical axis is the area under the curve. So the higher it is, the fewer mistakes you make. On the left, the dots are the performances of FBI examiners, people who are trained to recognize faces on a certain data set, of course. And on the right, it's a performance of four computer vision algorithms for face recognition that the authors trained in different years. And what you see is a couple of things that are interesting. So one is, of course, the examiners, the red dot indicates the mean performance of examiners. They're very good. However, you can get unlucky, and there are plenty of examiners who perform really poorly. So those are all the dots at the bottom of the carrot on the left. In the middle, you see random people that are called to testify in court are not reliable at all, so avoid them. On the right, you see the good news, which is every year, computer vision, our field, has developed better and better, has improved the algorithms to the point that now, 3 years ago, in 2017, 4 years ago, the performance was better than the average examiner. So that's good news. And so the conclusion of the paper is, so this is, sorry, I had a beautiful animation to tell you all that I've told you already. So the news or the conclusion of the paper is, don't let people, even examiners, do face recognition. You should always have a machine, a good piece of software to help them out. And so that's a, now, another observation is, why are people inaccurate? And it turns out that people are not only inaccurate, but they're also biased, and not because of malice, it's because of signal. So people get trained to recognize faces in a certain ethnic mix, that is the ethnic mix within which they live. And so if they are asked to recognize a face that belongs to an ethnicity that they're not familiar with, they are going to be quite inaccurate. And so this is what these plots are showing them. For the interest of time, I'll skip ahead. But basically, it's the point is that you will not recognize well people that you of an ethnicity they're not familiar with. And so you have a tremendous bias in accuracy across different ethnic groups. Most people are that way. Now, the good news for machine learning is that when you discover bias in an algorithm, you can fix it. And so it's not easy to fix biased people, and we know it by personal experience. It's not easy to detect bias in people because people will not want to be examined and measured. And it's also expensive and complicated. It doesn't scale well, but you can measure and benchmark a machine. You can find biases in a machine, and you can fix it. You can collect more data, annotate it well, and we are engineers and we know the process. It's painful, but it gets there. So, so that's the bright ray of light that is at the horizon. It motivates us to move forward and do a good job. So if you want to fix bias, then you need to learn how to measure it. And the other thing is you need to understand what are the causes of the bias, because in order to fix something, you need to know why is it going wrong. And as it turns out, it's a crucial aspect. And when we spend too long in the machine learning domain, we get trained a little bit in the wrong way. Namely, we tend to look at correlations and we forget about causation. And so today's talk hopefully will rebalance, will reestablish the balance, and will bring back causation as an important thing that we need to be aware of and study. So I will focus today on face recognition and face analysis, in fact, gender classification, because these are topics I know better. And so I hope to then be able to generalize a little bit to other systems. Now, in face recognition, there is an institute, the National Institute of Standards and Technology in the US, that has a huge experience in testing algorithms. And so every few months, they test hundreds of commercial and academic algorithms. And they produce curves such as these ones, which the common person in the street cannot understand, but of course we are trained to understand. On the vertical axis, you have a false non-match rate. So the algorithm here is asked whether two faces are of the same person. So two photos are the face of the same person or different person. So on the vertical axis, you have the false non-match rate, which is when the two faces belong to the same person, how likely is it that the algorithm will say not the same? And on the x-axis, you have a false match rate, which is when two faces belong to different individuals, how likely is the algorithm to say that it's the same person? And as you know, by moving a certain acceptance threshold, you can trade off the two errors, and therefore you can generate a curve. And here what NIST has done is something very useful. They have really amazing data sets, which they will not disclose to the outside world for fear that their tests are polluted. And they can divide up their test set into different ethnicities and different genders. And so here you see a number of curves, and I have labeled a few. So the curve on top, the red curve is Native American females. In the middle, you have Asian females, the green curve. At the bottom, you have African American males. And the bottom left corner of the plot is the best performance, the lowest false non-match rate, and the lowest false match rate. So you see here a couple of things. One is that these algorithms are truly spectacularly good. The data set here is a data set of arrest photographs, so they're on average well lit and frontal. However, the people do change in time. Their appearance changes quite a bit. So the photos belong to of the same person maybe 10 years apart, and there may be different hairstyles, different expressions on the face, etc. So it's a fairly challenging data set, not the most challenging. And what you see is that the false match rate can be as low as 10 to the minus 5. So that's more or less where you see the dot for the African American male. So this line here is 10 to the minus 5. And the false non-match rate can be 0.2%. This is 0.2% or 0.1%. So it's truly super good for African American males and females. And it's still good, although not as good for Native American females. So this would be a 3% false non-match rate for, again, 10 to the minus 5 false match rate. Okay, so the performance is very good overall, but there are differences between genders and ethnic groups. And so the question is why? You know, what is different between these different photographs? Is it that we don't have enough training examples for Native Americans? Probably. Is it, you know, why are African Americans working better than Caucasians? We don't know. And so the question is, how do we find the reason? So here is another example, and I'll skip it in the interest of time. Let me not worry about it. So academics have started caring about this about 3 or 4 years ago. And here I would like to go in detail through one study that has gained a lot of attention in the press. It's called Gender Shades. It's by Joy Bulamwini and Timnit Gebro, 2018. And what they did at the time was studying not face recognition, but gender classification, which is a much easier question to study because it's easier to train the algorithms, etc. And you need smaller data sets for testing. And in order to try to understand if there was bias, they collected images of 4 groups, light-skinned females, light-skinned males, dark-skinned females, dark-skinned males. And how did they collect them? Well, they downloaded photographs from the parliaments of 6 countries. They took 3 Scandinavian countries to get lots of light-skinned people. And so they took Iceland, Sweden, and Finland. And they took 3 African countries for the dark-skinned people, Rwanda, Senegal, and South Africa. So they got about 1,200 faces this way. And when they classified the faces by gender, they found a higher error rate for dark-skinned females than for the other groups. So here I'm comparing the error rate for dark-skinned females versus light-skinned females. And as you can see, there is a big difference. And so the newspapers picked this up and generalized it a lot. So they, instead of saying, well, you know, for parliamentarians in Rwanda and Finland, the classification rates are different, they said, oh, face recognition. In fact, they said AI is bad for dark-skinned females, is biased against dark-skinned females. So it was a very broad generalization, but it got the attention of everybody. So what's going on here? And and it was a group from IBM that pointed out that the reason may be simple. It may not have to do with ethnicity. The data set samples mostly gender typical hairstyles, namely women with long hair and men with short hair. Why does it do that? Well, because parliamentarians are dressed conservatively, and so the women will want to have long hair and the men short hair, and you don't find the Jesus Christ look amongst the male parliamentarians in Finland or in Sweden, and vice versa. There are very few women with very short haircuts, etc., with one exception, namely amongst the African females, the short hair style is a popular professional, clean-cut look, and so the data set is biased because it does not sample non-typical hairstyles for light-skinned people and for dark-skinned men. It does a good job, of course, for dark-skinned females. Now, it turns out, and this was the hypothesis of the IBM group, that if you have a gender classification algorithms, it might rely in part on hair length, and therefore it might make more mistakes on dark-skinned females because they're only ones where you have sampled both hairstyles. Okay, so here you have a correlation of hairstyle with ethnicity, which maybe is influencing the measurement. So what we see here is that an observational study, namely you pick random people out of a certain population, and you measure the performance there. There's observational study is fine if you are interested in the performance on that population, but it's difficult to draw conclusions that generalize to new populations. You don't know what's going to happen. And this correlation is not causation point, is driven home by a funny article by Messerly, who showed that there is a high correlation between the number of Nobel Prize winners in a country per 10 million population and chocolate consumption. And so it's unclear whether winning more Nobel Prizes induces the population to eat more chocolate, or eating more chocolate will cause people to win more Nobel Prizes. And intuitively we say, well, neither is true. Maybe there is a common cause. So maybe wealth in a country induces more chocolate consumption and also promotes more science. And I think you all know about the work of Judea Pearl, and I'm not going to go through this, but basically there is a good way of thinking about causation, and there are algorithms for establishing cause and effect given data, and the point is you need to run experiments. Okay, so let's get there. So what do you do then? And so here are the faces, and so the question is, we would like to know if being female and having a dark skin is the cause of the algorithm failing, or if the cause is a different one. And so that's how do we do that? And so again, in order to do it, if you read Judea Pearl, it's important to be able to carry out experiments. And what is an experiment? An experiment is a study where you compare the performance of the algorithm while you modify one variable at a time, okay? And so the question is, how do you modify one variable at a time if you're sampling from a population where there are all of these correlations in there? And so there is an example comes from the work of Marianne Bertrand and Sendil Mullainathan at Chicago. And this is in the social sciences. The question here was whether people of African-American origin have a tougher time on the job market than Caucasians. And the way they addressed this was sending CVs and applications to companies that were advertising for jobs. And the applications would be the same, but they would replace the first name of the applicant. And so they would use the names Emily and Greg and equivalents to induce the perception of a Caucasian applicant. And they would use the names Lakisha and Jamal to induce the perception of an African-American applicant. And what they found is that even being the application, there would be a 50% decrease in the rate of interview requests if the applicant was African-American. And so here they could prove that the name, at least this difference in name and therefore the perception of ethnicity had an influence on the, and so there was the bias could be proven this way. So the IBM team had the same idea. And so what they did, they used image processing techniques for changing the skin tone of the images in the data set that Bulamwini and Gebru collected. And they found that there was no effect of skin tone. Okay, so that's what they found. Now, however, these images look a little bit artifactual. And the question is, how would you study the effect of hair length? How would you study the effect of age and other quantities? And so how can you carry out an experiment in the field of computer vision where the idea is that you have to change one variable at a time, okay? And so what we thought we would do would be to piggyback on the explosion of technology for generating synthetic images and try to synthesize images that have the variations we need for our experiments. And I'll show you how we did it. So as most of you know, the most popular techniques for generating synthetic faces right now is using GANs. And that's what we did. We took GANs from NVIDIA, which is perhaps the best team that is producing software for generating GANs. And so we took a pre-trained generator. And on the left, you see a vector Z or Z, which is a vector of 512 variables, random variables, that gets fed into the generator, and the generator will produce the image of a face, and the face will be different when you change the input vector. So you have a latent space on the left, Z or Z, which is like the essence of the identity of the face, and then it gets unwrapped into an actual image by the generator, okay? Now, if you use this mechanism, you can generate random faces and they look good, but how do you modify selectively one attribute at a time? And so the idea is very simple. If you have two samples in latent space, Z1 and Z2, and let's suppose that one is male and one is female, it turns out empirically that as you move slowly across Z space, the face will change slowly. And so there must be a point, sort of an intermediate value theorem, where there is a transition between female and male, at least one point. There could be many, but at least one. And so if you find this point by, for example, projection, then you should be able to find a plane that is normal, a hyperplane that is normal to the line, and you should be able to find the direction of maximal change between male and female, and then also on the plane directions that are independent, where you can change other parameters and not influence male and female. And so indeed this works, and so you can manipulate different attributes without changing too much of the face, too much of the other attributes. And so I'm going to get into it a little bit more. So here you see what can go wrong and what you have to worry about. So look at the top strip of 7 images. If you move your eyes from the top right to the top left, you will see the image changing from female looking to male looking, although it's the same physiognomy. So it could be 2 siblings from the same family, and they go from female to male. Now, sorry, so I said it wrong. So the manipulation here was changing hair length. And so, however, what happens is that as you change a hair length, since hair length is correlated with gender, then also the physiognomy changes from female to male. And you see that very clearly in the top strip. If you move your eyes from right to left, the hair length decreases, but also we go from female to male. Now, as you might imagine, when you have these correlated variables, it's like 2 vectors, 2 principal directions that are not orthogonal in the latent space, right? And so the idea is if you figure out ways to orthogonalize your directions, then it would be able to control one aspect at a time. And of course, all of you have gone through linear algebra, and so all of you have an intuitive notion of how this could happen. And so I'm not going to go into the details here. But if you look at the second strip and you move your eyes from the right to the left, you will see that the face remains feminine looking, and the hair becomes shorter. Okay, so you can control both. Now, the same is true for the strips that you see below, and I'll let you check them out for a second, and then I move on. Okay, and so yeah, all of my special effects. Now here, for skin color, we didn't find obvious correlates, and so whether or not we were orthogonalizing, we didn't see much of a difference. And so it looks like skin color was naturally more independent than other variables. Okay, so now once we have this tool, what do we do to construct an experiment? And so we do the same thing that drug companies do when they test the efficacy and the safety of a vaccine or of a drug. We have matched samples, namely when we want to compare dark skin and white skin, we try to have two faces that look identical apart from the color of the skin, or as close as possible. And so the equivalent in the drug industry for a clinical trial would be having, if you have a white male age 70 in the control group, then you have to have a white male age 70 in the test group, right? And so here, what we do is we generate what we call a transect, which is 8 faces where we modify 3 variables. And so 2 to the 3 equals 8. And we start from an initial face, which you can think of at the center of a cube. And then moving along the hair length, gender, and skin color, we generate 8 faces that are like the vertices of the cube that sample these 3 directions and are otherwise matched, okay? And so we generated 1,000 such cubes, 1,000 such transects for a total of 8,000 transects. And here are a few more examples of transects. Okay, so there is a great diversity of appearances and backgrounds and so on, but each time a face is matched, same background, same viewpoint, same lighting, etc. And so this ensures that any fluctuations in the performance of algorithm due to background or due to eyeglasses or whatever, the fluctuation should affect every single face the same way. And therefore, in the end, you can compare apples with apples. And that's the idea of the experiment. Now, you will be wondering, how does the algorithm know what the heck it is doing? How does it know that it's modifying the hair length or that it is modifying the gender? And so the only way you can do it is through human annotators. So of course, these faces have no ground truth. There is no real person behind these faces. And so our ground truth is the perception of human annotators. And so I want to go through this briefly. So the idea is that we have this latent space. You see it up there in the top left of the slide. And by sampling 5,000 random faces and having them annotated for 8 different attributes, some of which you've seen already, we can establish a set of level curves in the space, which we approximate with level planes. And so we have a global reference frame that allows us, given at any point in the space, it allows us to travel along age, along gender, along hair, etc. Now we can feed these trajectories or transects into the generator. And so here you see a hair length transect where from left to right, the hair length changes. Once these are produced, we cannot really trust the generator to have done a good job each time. And so what we do is we feed it back to the annotators to verify the performance. So the images that the generator produced are sent to new human annotators on the top right, and they will generate their annotations as to what these transects look like. And then they're fed the same images to the gender classifier in orange, and that's the algorithm that is being tested for bias. comparing the performance of the gender classifier with the annotations, we can get a measurement of bias analysis. So how do we annotate in practice? So there is all of you know about Amazon Mechanical Turk. Well, there is another service built on top of it called SageMaker Ground Truth, which we used. And it allows even professors to put together quickly a GUI for the annotators, like the one you see. So I did it myself in like 10 minutes. And then you can send out annotations for 8,000 faces, 5,000 faces, and get results within 24 hours or so. It's really, really effective. And so here is the skin tones. And so we use the Fitzpatrick scale for skin, which is a dermatologist's scale for skin tone to assess the likelihood you get skin cancer if you stay a lot in the sun. And so on the right, you have the buttons that the annotators click to rate the image. And on the left, you have a guide to explain what the different levels mean. So here is the GUI for annotating hair length. And as you can see here, we have 5 levels. And so very short, short, medium, long, and very long. And on the left, you have, again, a guide as to what very short, short, medium, and so on mean, right? And so we have it both in terms of length, centimeters or inches, and also how does the hair look like and what's the property of the hair. And so this is how we collect data. And so we have 8 attributes. And when we collect the data, then we can look at the reports of the different annotators. So here, each dot is one annotation. On the x-axis is a coordinate between the leftmost image. You have here a strip of 13 images on the top, right? And they go from female, middle-aged female to young male, whatever that means. And at the bottom, you see from -6 to 6, the 13 steps corresponding to the images. And for each step, we've collected 9 annotations, and I've scattered them around with some noise to be able to see them all so that they wouldn't overlap. And you see that they are quite well grouped around a certain value with a little bit of a spillover in the 2 nearby bins. So this is a typical behavior that we see amongst annotators. And so although there is no physical ground truth for these faces, there is a perceptual ground truth, which we can collect by having lots of annotators annotate the images. And after studying in a pilot study how consistent they were, we decided that 5 annotators would be enough. And we decided to take the median, or in fact, the mean of the median 3 annotations, some robust statistics recipe. And so here you see skin tone. For the same image, you see hair length annotations, and you see gender perception here. And so again, you see that for gender is a fairly sharp transition between female and male. Now, I want to say one thing, which is people worry about the question of binary versus non-binary gender. And so here we decided to use binary gender and accommodating non-binary with those in-between ratings. And for sure, things will change in the future. And so, I'm looking forward to understanding how to do it better. And one limitation is that there is no agreed upon scale for other non-binary genders. And so when you send it out to annotators around the world, it's unlikely that you will find people who agree on anything else other than female and male. So the best thing that best way that we found to address this is to have these intermediate steps. So you find every now and then that the annotators disagree with what the algorithm thinks it's doing. And so you see an example on the top left where the humans felt that the face is male, but the algorithm was convinced that it had generated a female face. And so when that happens, we discard the whole transect and we don't use it in our experiments. Now for hair length and gender and so on, here are a few faces. So short hair length on the left and long hair length on the right. And this is what you get from, so the sampler is the synthetic faces we use, and these are ranked by hair length. These are ranked by apparent or perceived gender. And so female, more female on the right, on the left, more male on the right, and ambiguous in the middle. Here is skin tone, lighter skins on the left and darker skins on the right. And then we also annotated for fakeness because we wanted to catch images that have evident artifacts due to the fact that the GAN is not perfect. And so we discarded all the images that people felt that looked fake, because then we thought, okay, maybe then the rating of gender and age and so on are not so good. Okay, now we have a method, so let's apply the method. And so let me start off with this kind of plots. You will see 2 or 3 slides with these kinds of plots, so get used to them. The first thing I want to draw your attention to is we have 4 data sets. So the top one is Celeb Bay HQ. It's a data set of celebrities. The second one is FFHQ, also mostly just celebrities. The third one is the PPB, the Parliamentary Pilot Benchmark dataset from Bulamwini and Gebro that we talked about before, the one from the 6 parliaments in Africa and Scandinavia. And at the bottom, you have where it's written transects. These are our synthetic images. So what you see is that so the skew on skin color is quite obvious on the first 2, which are popular. And so you see that they're basically only sampling people with light skin and very few with dark skin, while the PPB and transects are quite balanced by design. And so that's why those are good data sets. Now, the thing you find is that in hair length, all of these data sets are quite skewed towards gender typical. So if you look at Celeb and FFHQ, for female, which is red, you find only long hair, and for male, only short hair. Now, for the transects, we're able to balance it much more. For PPB, you see what I was talking about before, namely you have quite a few females with short hair, right? And we made it even more balanced in the transects data set. Now, things become interesting if you do an intersectional analysis where you separate out females and males with long hair, with light skin and dark skin. And so what you see here is that indeed for the celebrities data sets, the females are all wearing long hair. And so there is very few or none with short hair. While for PPB, there is a good sampling of dark skinned females with short hair, but there is terrible sampling, in fact, none of light skinned females with short hair. And so that's a problem. And for the transects, instead, we have a balanced sampling, which is very important. Okay, so when you go back to the measurements I was showing to you before and you disaggregate them for hair length, then what you see is that indeed in the PPB data set, a parliamentary data set, you don't find males with long hair, neither with light skin nor with dark skin. And so the error bars of the measurements are huge. So you can say nothing about the performance of the algorithm on long hair males. And the same is the problem with females with light skin and short hair. The error bars are huge, and so you can say nothing because there are too few. But you can say something about the performance of dark skin females with short hair because there are quite a few. By contrast, if you go to the transects, which is what we collected, we produced, then you can sample well. You have good error bars or small error bars on each one of these categories because they're all sampled well. And what you notice is that if you look at long hair females, the performance is the same. So there is no difference between having a light skin and a dark skin. And if at all, on the short hair females, the system performs better for dark skin females than for light skin females. But the main effect is that the system makes quite a few mistakes. So, so once you aggregate back to the original experiment, what you see is that the effect of higher error rates for dark-skinned females goes away because you have now balanced the data set, and all the different boxes have been sampled, with light-skinned males with long hair, etc. And so you see overall a higher error rate for males, which you would expect because now you have males with long hair, and a higher error rate for light-skinned females, but much lower for dark-skinned females. Now, the PPB data set is very focused on middle-aged people, and so it doesn't sample younger people. And it turns out that if you sample younger people, you find another surprise, which is that for young-aged people, there is an enormous bias where males get confused with females all the time, while females are correctly classified. So that's another lesson. So there are many variables involved, and depending on which group you focus on, you can make claims that are at odds with each other. So here you could say that the main effect for these gender classification algorithms is biased against males, and it's biased against young males. Okay, so now another thing that you find in the paper, which I will not go through, is you can carry out regressions to see what is the effect of different variables on classification accuracy. Okay, so I want to come to a close. So I want to tell you about one last thing, which is after we completed a study, we ran a review of all of our images, and we found some interesting correlations that had escaped us at the beginning. For example, here, what you find is at the top that as you make the hair length longer for males, they also tend to sprout a beard. And so I don't know if you remember, but long-haired males had a fairly good error rate or low error rate, surprisingly for us, unlike short-haired females. And the reason we think is because they tend to have a beard in our synthetic images. So this is something we did not control for, and we should have. And so if somebody wants to pick up our study and use it for industry, for testing industry systems, they will have to spend a little bit more time looking for all of these other funky correlations and orthogonalizing for them. Okay, so that's one thing. The second one at the bottom, what you see is that equivalent faces of males and females in the same transect have different frequency of earrings. So it's quite unlikely for a male to wear earrings and quite likely for a female. And so that's what the algorithm is doing. Now, and so the question is, are earrings part of the characteristic of being female, or are they orthogonal and they should be taken away from the test? And so this is up to whoever runs the test. They have to come up with a definition of what do they believe is part of the identity of being female. And if a high frequency of earrings is part of the female identity, then they should keep them. And if they feel that it's not, then they should remove them, orthogonalize them away. So that's another point I want to make, which is you need to think hard about what do you mean for different characteristics, and then you want to check that what you mean is being implemented by the synthetic method. Okay, so last slide. So I hope I convinced you that one has to pay attention to how we carry out our studies. Our traditional studies in computer vision are observational. We sample images in the wild, and what happens then is that a bunch of different variables are tangled or correlated together. And so it's very difficult to draw conclusions on causal effects and saying, oh, my algorithm works better for outdoors pictures than for indoors pictures. God knows what else is there that is correlating with outdoors and so on. And so the only way to come up with causal statements is by carrying out experiments, and experiments means modifying one variable at a time while keeping everything else constant. And this allows you to untangle these funky correlations between different variables. Second point is that when you intersect different characteristics, for example, you want to consider gender, hair length, and skin color, you get lots of boxes. And if you sample in the wild, you may not be able to sample all the boxes. For example, we know that it's difficult to find middle-aged women with short hair. And so in order to sample those boxes and know how your algorithm works in those conditions, you've got to synthesize images. And the third one is, you saw my approach or our approach. It's generating synthetic images and relying heavily on human annotations. And it turns out that both are reasonably inexpensive and fast. And so it's much better than sampling from the environment where it takes months or years to collect a good data set and annotate it, and leave alone all the implications for privacy and human dignity and all of that. And as the last point, there are always residual correlations. And so if you want to make a good system that samples, that measures properties well, then you've got to pay attention to those. Okay, so thank you very much. These are my collaborators, and I will be happy to take questions at this point.